So you have a question about fluid mechanics. Why does the pressure increase with depth, even if the container is narrow or wide? It's one of those questions that really requires you to work it out. What I want to do is think about a container, and let's say you fill it with water. So let's say you fill that with water. What we want to do is try to figure out, okay, how does the pressure change? We could have an atmospheric pressure, right? So it's the same pressure. The pressure as a function of depth works with the atmosphere as well. But let's just say that we'll take that as a given. So we're not going to consider the atmosphere for now. Let's say that what I'm going to do is say there's a pressure from the outside. So if you watch the weather, there's some pressure reported every day. That's at the top, and we want to figure out, okay, at the very bottom of this container right here, what is the pressure at the bottom? And I'll say that's the total pressure at the bottom of the container. We can kind of guess that it should be higher than the atmospheric pressure right here, right? So this pressure right here is some number, but we can kind of guess that as you go down in the container, that the water is going to add. And so you have firsthand experience of this, right? If you are in the ocean, you get in the swimming pool, right? The further you go down, you feel more of a pressure. What we'll do is try to figure out what this is, right? So how does this actually vary with depth? So this is the bottom of the container. And what I want to do is think about, okay, pressure. When we say pressure, what do we mean? Pressure is some force over some area. And for a moment, let's ignore the atmospheric pressure. And what I want to do is just consider what the water is doing. So the force, right, that's acting on the bottom of the container is the weight of the water. If you just imagine you're really tiny, you go down at the bottom of the container, what's pushing you down is the weight of the water is pushing you down. So that's the force that's acting over what area? Well, this area. So there's this area of the container at the very bottom. That is the area that we're dividing by. This force here that we're saying force over area is really the weight of the water divided by that area. How are we doing so far? Kind of following along? Ask me questions while I go. So if something's not clear, you're following along. So you have the weight over the area. So then let's just think about, what do we mean by weight? Well, the weight is the mass of the water times this g. If you've seen this before, then this might make sense. But if you've not seen the idea of a weight, it comes from F equals ma, essentially. This is the ma. The a is the acceleration due to gravity in this case. When we say weight, we mean the mass of the water times g, 9.8 meters per second squared on the surface of the earth. Again, divided by a, the area. We just keep breaking this down, right? So when we say mass, what do we mean by mass? By mass, I mean, well, what if I take the density of the water and then multiply by some volume? When I say mass, what I mean is the density times volume. Density is mass per unit volume. So if you multiply by volume, you'll get the mass, right? So then that multiplied by g divided by a. Now we're going to break down this volume. So when we look at this water, what do we mean by the volume of the water? Well, there's some height to this water. So the volume of this water is, if you just take that area and multiply by the height, that's your volume. So that usually works with volume. If you just have a cross-sectional area and multiply by some distance, height, then you get volume. So what we're going to do is rewrite this, right? So we can say density, and instead of volume, we're going to say times the area times h, and then don't forget g, divide by a. And so notice what happens here is that the areas will cross out, and what you're left with is equal to rho h and g. Oftentimes this is just, I remember it as rho g h, right? It doesn't matter which way you multiply, it's the same thing, but I just remember it as rho g h. So that's just the pressure at the bottom of the container due to the water. And remember, we have the atmospheric pressure at the top. So when we want to write total pressure, we write the pressure from the atmosphere plus this contribution due to the water, right? So rho g h. So if you want the total total pressure, that's how you get it. You get total pressure by taking the atmospheric pressure and you add the contribution from the water, right? So rho times G times H. Now, to your question, notice that it's a long story to your initial question. This is why it's only a function of height, because there are certain parameters that do depend on the area, the wider the container. But notice that the wider the container, you have more force, more weight, more mass, right? More volume, right? So all those things come into play, but you're also dividing because ultimately the pressure is dictated by an area. So the wider your container, you're making the area bigger. So those two factors cancel, right? So literally in the math, that's why the A's here, if I highlight this, right? So these areas drop out because they are coming from different things, right? So the area is a part of the weight argument, right? So up here, this weight had an area in it. That's what we're showing. And then of course, area has an area in it. That's why the areas cancel. So if you look at the pressure in a fluid, it only depends on the height, and that's why.